exercise 3, and this is on the Trefoil Knot, or Trefoil Knot. I'm not sure exactly how to pronounce it, but I will call it Trefoil Knot. So the view of the Trefoil Knot shown earlier and copied below, so I copied it here from earlier video, is accurate, but it doesn't reveal the whole story. So here's the parametric equations of it, and it looks like this. So yes, this is a bit next level. It's hard to tell exactly how it looks or behaves from like different angles and so on. So we'll have to look at that. Alright, yeah, so this is a trefoil knot. So we're asked to use the following parametric equations to sketch the curve by hand as viewed from above, with gaps indicating where the curve passes over itself. And here, that's another part from this angle right here. We don't know which one goes above, which one's below. Is this behind it? Is this in front of it? And so on. So here's the parametric equations. These are the same ones. Here I just copied from the earlier section, but now here's from the actual exercise. So x equals to 2 plus cosine 1.5t, all multiplied by cosine t. And then y is equal to 2 plus cosine 1.5t, and then all of that multiplied by sine t. And z is equal to sine 1.5t. And we're asked to do this. So start by showing that the projection of the curve onto the xy plane, so basically for the vertical projection straight down to the horizontal, has polar coordinates r equals to 2 plus cosine 1.5t, and theta is equal to t. So yeah, and this is polar coordinates. So r varies between 1 and 3. And that's because right here, if this is the polar equations, r equals 2 plus cosine 1.5t. Cosine is always going to be between 1 and negative 1 as the minimum and maximum. So it's going to be between 2 plus plus 1, which is 3, or 2 minus 1, which is 1. All right, then we're asked to show that the z has maximum and minimum values when the projection is halfway between r and r equals 1 and r equals 3. So it's somewhere t in between those. When you have finished your sketch, use a computer to draw the curve with viewpoint directly above and compare with our sketch. So basically, we're asked to sketch by hand the vertical projection onto the xy plane, and then compare that with a computer. Then use a computer to draw the curve from several other viewpoints. And we're given a hint here. You can get a better impression of the curve if you plot a tube with radius 0.2 around the curve. Use the tube plot command in Maple, or tube curve or tube command in Mathematica. These are some mathematical programs, pretty advanced. I think you have to like download and so on, but I'll just use GeoGebra and work around it as I can. All right. So anyways, let's take a look at the solution. So the projection of the curve onto the xy plane is given by the parametric equations, and we just take the x and y components, and then we just set z is equal to 0. So if we set this equal to 0, then that's just going to be the graph right on it. So I'll put that for completeness. Yeah, for completeness, I'll just add this here. The solution panel didn't include it, but I like including it. This equals 0, like that. Alright, and now we can convert these polar, or these equations right here, these parametric equations, to polar coordinates by finding the distance from the origins. If we recall from my earlier video, again, polar coordinates are pretty straightforward. So if I'll draw this xy axis, so we're just doing it in 2D, like this. So if we have this right here, this is the x, this is the y right here, and then, so to get polar ones, if we have the point right here, this is on this point right here is going to be, so basically if we draw this like here, so polar ones, we just convert it from a, I'm going to put this all the way there. Yeah, just fix that up. Yeah, so if we have this point right there, and I'm going to call from, this is the, I'm going to call this distance r. So this is the distance from the origin. I'm going to draw this angle right here. I'm going to call this theta, and I'm going to set this equal to t, and we'll show that it actually is t, and basically, because again, we're converting it into polar coordinates. So if we draw it like this, this is the top side. So this is the y. This would be the y component, and this is our x, y point. So the y is going to be equal to our parametric equation, 2 plus cosine 1.5t, and then times it by sine of t, like that. And then this is the x, and then this x is equal to this equals to 2 plus cosine 1.5 t times by cosine t. And again, this is the origin, so put a O there, or 0. So now by the Pythagorean theorem, Pythagorean. All right, here I just wrote that, yeah, Pythagorean theorem. So we're going to have r squared is equal to, well, x squared plus y squared. So the square of the sides of a right angle triangle is equal to the hypotenuse squared. So we have r squared equals x squared plus y squared. So now this equals to, plug in the x. X is going to be 2 plus cosine 1.5 t. I'm going to square this, and cosine is going to be squared. All right, here I just shifted it over, try to fit this all in one line. So now what's going to have the next one is going to be the y. The y squared is going to be, well, 2 plus cosine 1.5 t, and then sine, and this is squared, sine squared t. So we have this, and we could take out the common factor right here. This is just the same one, so we could factor that out. So this equals to 2 plus cosine 1.5 t squared. Factor that out. Now we're going to have and so factor out, we're going to have cosine t, cosine squared t plus sine squared of t, like that. And now this just a Pythagorean identity. This just equals to 1. So that all vanishes. So what we're left with is, I'll move this over here. We're left with is r squared is equal to, and now we have 2 plus cosine 1.5 t all squared. Now we can just square both sides. We get what we're going to end up having is an r equals 2, well, plus or minus, but we're only just going to look at the plus side because it's distance. So it's going to be plus or minus, and now we're going to have 2 plus cosine 1.5 t, like that. And we'll only take the positive. I'll also put plus or minus because it's very interesting. I always get 2. But anyways, so we take the plus because we just want the distance from it. So this equals to 2 plus cosine 1.5 t. So that is our polar equation. And this is in terms of t, but then again, t is just going to be theta, and we could show this, and we can show this by basically saying also note, I'll put this not caps lock. Yeah, also note, if we take right here, so I'm going to do tan of theta. So tan of theta there. Tan of theta is going to be, also note tan of theta. This equals to, well, it's going to be the y over the x. So this is a opposite over adjacent. So that's going to be y over x from the graph. So that's our theta. So y divided by x. And if y and x are the parametric equations, this equals to, well, the y is going to be, and I'll move this down. I'll move this down right here, so I have some room to operate. So, yeah, this is going to be 2 plus cosine 1.5 t, and then this is going to be sine. The y has the sine. So remember, the y has the sine, and then the x has the cosine. So divide this all by 2 plus cosine again, 1.5 t, and this is going to be cosine t. So then this just cancels out, and yeah, if that cancels out, we're left with is, well, this just equals to sine. Yeah, this just equals to sine over t. Yeah, sine t over cosine t, and again, that's by definition just tan t. So again, that's the opposite of adjacent. Opposite over hypotenuse divided by adjacent over hypotenuse. Hypotenuse cancels, and we'll do that actually for completeness, just so we can prove it all in one go, as opposed to just telling it's that. What I'll do is put it there. I'll cross this out. And this equals to, well, this is opposite over hypotenuse, and the hypotenuse is r. So again, the hypotenuse is just r, so we go y over r. This equals to y over r divided by x over r, adjacent over hypotenuse. So then r is cancelled, we just get y over x. So in other words, this equals to, yeah, well, this equals to tan theta, but again, this is, again, tan of t as well. So this is, yeah, we could just erase this. Again, that was just a double check there. But again, this just equals to tan. Again, let's just show you the same thing. So this equals to tan t. So in other words, what we have is theta. So tan of theta is equal to tan of t, because that's just, again, definition slash just using basic trigonometry. So thus, what we get is right here, or yeah, this is what we get is theta is equal to t. Yeah, so we could just replace theta with t. Again, that was just an extra double check that it's all everything matches up. Anyways, so thus our parametric equation is, our polar equation for the parametric equations are r equals to 2 plus cosine 1.5 theta. So again, just for completeness, just put theta instead of t. Just so indicate it's an angle, and again, the same thing. And yeah, I'm not even sure you even need this, because it's just my calculus book stated that, but again, it's pretty straightforward. Theta is equal to t. Because you just set it to it, you're just converting it into polar coordinates, and it's always going to be just when you're graphing it like that. Alright, and now we're going to start graphing stuff. So at theta equals to 0, so let's just start from the beginning as the parameter t or theta is equal to 0. We have r equals 3, and r decreases to 1 as theta increases to 2 pi over 3. And we can show this, well, basically at this is a 1.5 theta, and again, because that's it's that, so at 1.5 theta, this just equals to 3 over 2 theta. When this whole thing is equal to 0, then cosine of that is just 1. Then what we'll get is a r equals to 2 plus cosine 0, that just equals to, well, 2 plus 1 equals to 3. So that is at the beginning. And we can show this. I'm just going to recall. I'm going to draw a bunch of stuff here. So recall we will use this for throughout this setup here. So I'm going to recall the graph of cosine. I'm going to go this super far. And this is going to be theta. And this is going to be cosine theta. Let's put it like this, cosine theta. So we have cosine theta. And I'm going to go all the way up to 6 pi, because we will use 6 pi. I'm going to go, if this is 2 pi, this is 4 pi, then this is going to be 6 pi. So, and this is at 1. So that's at 1. Now we need to extend this one. Extend it all the way down to -1. Just so we grasp this all. And then this is in between, this is a pi. So it goes like this, and then it goes like, and it has to go all the way back up. So that it doesn't go like that. Yeah, if we recall, this has to go all the way back up to here. So it needs to, so then this would be the minimum there. So it's going to go like this. And then it goes like that. And same thing here would be at, this is pi, 2 pi, this is 3 pi. And it needs to go all the way down, and then go all the way back up. So all the way down, and this is a 5 pi. And we're just going to graph it for all these specific points. Or, yeah, just get the values there. So this needs to go all the way to the bottom. And I'm trying to draw it neat. Alright, it goes like that. And then goes up like that. Goes up, and there it is. Yeah, I'll fix it up. Alright, so here I fixed that up, and now the next one is, this is, so it starts off at 3, and it decreases to 1 as theta increases to 2 pi over 3, and in this case here, so when 1.5 theta is equal to 3, well, just equals to 3 over 2, this is 1.5 is 3 over 2 theta, again, this is just, well, theta is equal to 0. So that's theta is equal to 0 as our parameter, our polar coordinate parameter now. And then theta goes to 2 pi over 3, and we can see that, well, we'll just set it as, we go all the way to this -1. So it goes from the peak 1 all the way to the minimum -1. So at 3 over 2 theta is equal to pi, what we get is, well, what happens here is the theta, we'll just move this over there. So then means theta is equal to, move the 2 over there, and then the 3 at the bottom, and so on. So we're going to get 2 over 3 pi. So 2 over 3 pi like that. And hence why we have this part right here. I wrote that there, 2 pi over 3. So then r is going to be now r is equal to 2 plus cosine of this right here, cosine pi, because we set the whole thing to pi, like that. And now this equals to, well, this is negative 1, so 2 minus 1 equals to 1. Yeah, so it basically goes from at the theta is equal to 0, it's at maximum 3, and it goes down until r is equal to 1 at theta is equal to 2 pi over 3. So there it is. All right, now going further, so we have the 2 points right here. So it starts at 3, decreases to 1, and I'll go another pi. So for 2 pi over 3, for theta is greater than or equal to 2 pi over 3, and all the way to 4 pi over 3, r increases to r again. So it's going to increase again. So when here you're going to increase to 1 again, then r is going to decrease to it increases to 3 again, then it decreases to 1, increases to 3, decreases to 1, increases to 3, because again we're dealing with sine wave. A cosine just goes up and down. So and then r decreases to 1 at theta is equal to 2 pi, and increases to r equals to increases to 3 at theta equals to 8 pi over 3, decreases to 1 at theta equals to 10 pi over 3, and completes the closed curve by increasing to 3 at pi equals 4. So it's 2 loops, but this 6 pi is dealing with this is the recall there, but this is actually dealing with 1.5 theta. So for completeness, just so we don't get confused, I'm going to put this like this. This is at again, this is 3.5 theta. 3 over I'm just going to because it's pretty straightforward. This is just for cosine, but we're dealing with that. So I'm going to put this in circle. So we're not actually using. We're not going to be using these variables. Are not associated with these in any way. I just have those for basic cosine. But now we're replacing theta with 3 over 2 theta, or 1.5 theta. All right. So basically for 2 pi over 3, and I'm just going to show you how all these. This is for my calculus book solutions manual, and I'll show you how this is all correct. And they basically go every pi. So the next one is and so the next one is 4 pi over 3. But to get that, what they actually do is at 3 over 2 theta, at that when that equals to 2 pi. So it's going to increase again. And in other words, we can solve for this one. Theta is equal to 4 pi. Move the 2 over to the other side, 4 pi over 3. Hence why you get this number, what they get that. And then what we end up having is r is equal to 2 plus cosine 2 pi. Cosine 2 pi, which equals to 2 plus, 1. So we know here, this is just 1. So there it is. That's 2 pi. And you can see the idea. I'm just going to, for completeness, I'm just going to go over all of them. This equals to 3. Like that. So it increases there. And then the next one is at 3 over 2 theta is equal to 3 pi. Then we're going to graph these all later. So then the theta is going to be, 3's cancel. Then move the 2 over to the other side. This is going to be 2 pi. And again, that's hence why we get this one here. So it's going to decrease. And this is at this segment, so we're going to subtract by 1. All right. So you get the pattern there. So r is equal to 2 minus, this is going to be plus cosine 3 pi equals 2. Let's erase this. Now, let's erase it. This equals to 2. Things messing up. Okay, 2 minus 1. This equals to 1. So hence, at theta is equal to 2 pi. It decreases to 1 at theta equals 2 pi. So that's what we have. Now the next one increases to 3 at theta equals to 8 pi over 3. And you can see the pattern. We just add another. This one is if this was 6. We add 2 pi each time to this top part. 2 pi over 3. I mean. So the next one's going to be 6 pi over 3. That goes 2 pi. Then it's going to go 8 pi over 3. Then 10 pi over 3. But anyways, let's just keep the same pattern up. So this is at 3 over 2 pi is equal to 4 pi. So then theta is equal to, well, this is going to go move it over there. So it's going to be 8 pi over 3. Then r is equal to 2 plus cosine 4 pi. This equals 2. 2 plus 1 equals to 3. And again, you can see exactly why my calculus book, calculus manual solutions manual stated all this. So you can see right here, increases to 3 at theta is equal to 8 pi over 3. So increases to 3, and then that's when 3 over 2 pi is equal to, well, 4 pi. So we get this 1 then, the maximum. Then we go to another minimum, we'll do 2 more. So the next one is 3 over 2 theta is equal to 5 pi. So this would be minimum. All the odds are minimum. This goes to theta is equal to, I move it over, yeah, the 2 over is 10 pi over 3. And we get r is equal to 2 plus cosine 5 pi. This equals to 2 minus 1 equals to 1. So it goes 3, 1, and so on. And then every 2 pi over 3, or every pi for the 3 over 2 theta. This is going to be cosine 5 pi. And yeah, so that is what we get there. Let's double check all this. This equals to, yeah, so decreases to 1 at theta equals to 10 pi over 3, and then completes a closed curve by going back to 3 at theta equals to 4. So this is basically 2 full curves, and now it's going to go all the way back. And we'll draw this out and show you how it goes, closes the curve. It's going to be 3 over 2 theta is equal to 6 pi. And that's because after, let's see, if we just go, let's see, this is a 2 pi. So because the thing is right here, we start off at 1, and then it goes to 3. Actually, you start off at 3 here. And then when theta is equal to 2 pi right here, we get to 1. So we never actually, so this one right here. So this is the first loop. So here, we start off at 3. Yeah, and yeah, at 6 pi, this is just going to be, well, 12 over 3. That's just 4. We can simplify it just because Kekul's book was doing that, so I'll just go 4 pi. Like that, or just 12 over 3. So every 2 pi over 3, that's the new point we're looking at, where we get new minimum or maximum. So we get r is equal to 2 plus cosine 6 pi. This equals 2 minus, 2 plus 1 equals to 3. So now we finally got back to it. Yeah, so because we finally got back to 3, the next one's going to go to 1. Yeah, so we started off at 3. Then we did a full loop at theta is equal to 2 pi. We got to 1, but that's not back to where we started from. And then we go another full 360 degrees or 2 pi radians, and we get back to 3. So now we're back, and then the next one's going to just go back to 1, 3, etc. So 2 full revolutions is equal to a full loop of this shape right there. And you can see that again. This is completes the closed curve by increasing to 3 at theta equals to 4 pi. And at theta equals 4 pi, we get 3 over 2 theta is equal to, well, 6 pi. So then there's a peak right there. All right, and now we can sketch an approximate graph in the figure. Yeah, we can sketch an approximate graph as shown in the figure below. So we can draw this manually just to see what we can come up with. So I'm going to go like this. I'm going to let's get some space right here. So this is our y. Okay. All right, so that's our y, and now this is going to be our x. Okay, this is our x, like that. All right, here I just fixed that up, and now what I'm going to do is I'm going to just draw dashed lines to help easier, because we know the minimum is 1 and the maximum is 3, so we should do that on every one of these axes. So I'm going to go 1, 2, and then 3, and likewise 1, 2, 3. Try to make it roughly the same. 1, 2, 3. And then 1, 2, 3. So we got like that. Now the first point is at theta is equal to 0. Theta is equal to 0, we get 3. So we just draw this right here. Alright. I don't know why it erased. Alright, here I brought it back up. I just undo erase. Anyway, so that's the first point. And now at theta is equal to 2 pi over 3. That's at, this would be at, yeah, that's actually at 120 degrees. And because again, pi is 180. So pi is 180, and then pi over 3 is going to be 60. So it's going to be, I'm going to draw this as guidelines. This is going to be 60. This is going to be 120. And then the next one is going to be, yeah, the next one's going to be, well, if it's 120, and then add another, yeah, this is 60 there, but yeah, this is 120. But then each time we're going to add 120 because we have right here 2 pi over 3. The next one is 4 pi over 3. In other words, we added a 2 pi over 3. So we add another 120. So that's 120. it's going to go all the way into, well, this is 60. Then another 60 is going to be across here. So again, you can see the symmetry like that. And like, I'm just going to draw it like that. So anyways, so that's the first point. And then the second point is at theta is equal to 2 pi over 3. And then that we end up with 1. All right, so that's at the point here. So it's going to go 1 here. It's going to go across here 120 degrees. It's going to be roughly around there. What I'm going to do is we need to draw this. I'm going to draw a curve like that. So it goes, or make it a bit bigger. Just going to make it like this. So it goes like that. All right, so it goes like that. Just do a rough estimate. Now the next point is going to be at theta is equal to 4 pi over 3. All right, so 4 pi over 3. And again, that's just adding another 120 degrees. Or we start with 180 plus 60 is us 240 degrees. And that's going to be over here, but it reaches a maximum at 3. So there it goes to 3 there. So now this has to go all the way across somewhere around here. So this one, draw a line like that. It's going to be somewhere around here. I'm going to draw it roughly here. So again, roughly like that. And I'll just draw this like that. So roughly like that. All right. Draw this a bit better. Connect to it. All right, so it goes like that. And now the next point is it goes back to 1. And it goes back to 1 at 2 pi. So it goes back to 1 at 2 pi. So it goes right here. So in other words, this is going to go like this. Like that. Or draw it a bit better. Let's say it doesn't get past. But anyways, it looks like that. And now the next setup here is going to go into 8 pi over 3. And to go from 8 pi over 3, it's just going to be exactly the same thing. It's going to be 120 plus 360, so that's going to be 480, I believe. So it goes all the way across here, but that goes up to at 3. This is 8 pi over 3, that goes to 3, and again, it's just the same thing. You're also adding 120 degrees. So it's going to go, but it's going to go all the way to 3 there. It's going to go somewhere around here. So it's at an angle, it's a bit lower than that. It's going to be a bit lower. It's going to be something like this. Anyways, so it goes there. And this goes all the way across there. I'll draw this a bit better. Okay, it goes like that. All right, here, just fix that up. Now the next one is at 10 pi over 3. That's another 120. It goes over here, but it goes to 1 now. So 1 should be around roughly here-ish. Yeah, around this area. So now we're just going to go all the way, loop all the way across. Just a bit better. It's going to go something like this. All right, here I just fix that up. And again, I'll draw the arrows. It goes like this. It goes down across here and goes up like that. So it goes down, up, and then this down like that. All right, let's check the next one is, that was at 10 pi over 3. Now the next one goes all the way to 4 pi, goes to 3 now. So it's going to go all the way, loop it all the way across here now. Yeah, so it goes all the way, loop across there, and then it recycles back the same setup there. So I'll draw a point like that. Yeah, so anyways, so that is roughly the shape that we got from here. And here is a better sketch from the solution manual. I just copied and pasted it here, took a screenshot of it. But yeah, this is just doing it manually. And here it is how it is. And you can see the exact same setup here. It goes like this, and then up and down. And this goes also like this. Yeah. Let's fix that up. Yeah, it basically goes like this, loops up, and then goes back, and so on. And it's yeah, it's slightly better. Yeah, no, it's better and has the center point actually goes over somewhere across there. But anyways, I could have just drawn this a bit more in the center there. So good enough. And now here, going further, we can determine how the curve passes over itself by investigating the maximum and minimum values for Z for t is between between 0 and 4 pi. And that's because in the question we're asked, how does it go over and below it, and so on. So it says first show that by yeah, it says right here. Yeah, going back here, it says use the following parametric equation to sketch your curve by hand with gaps indicating where the curve passes over itself. So the straight line would be on top, the gap would be the one underneath. Yeah, so yeah, going back down here. So we can determine how the curve passes over itself by investigating the maximum and minimum values for Z. And this is for the in 3D space. So this is a projection straight on the XY plane, but we want the actual three-dimensional projection, or the three-dimensional curve. So we need to see where the highest and lowest points are for the Z value. So and then highest maximum and minimum values for Z for t is between 0 and 4 pi. That's where this goes all the way until it reloops and goes back into the same cycle. So since z is equal to sine 1.5t, z is maximized when where sine of 1.5t or 3 over 2t is equal to 1. And again, going back to the curve, this was our curve right here. This is a projection onto it where z is 0, but here's just to double check, z equals 1.5t. And again, sine is minimum, maximum at basically at 1 and -1 is the max and min. All right. Note that well, what we have is, because we have 1.5t inside all of the sine and cosine and so on. So 1.5t, this is equals to 3 over 2t, and now this is equal to this is going to be maximized. And I know we need to find the maximum, but before we were dealing with the cosine. So this is a cosine. Now we need to do the same curve, but for sine. Because now we're dealing with the sine, and then from there we could find out what the t values is. So this is for z, this is for t is between 0 and 4 pi, except 3 over 2t is going to be, up to 6 pi. So you can just multiply by 4. So by 4 pi, so 3 times 4 is 12, divided by 2 is 6. So before we write these values, and I'm going to write this down, recall just the cosine. I'm the sine now. So the same thing as before. I'm going to draw this a bit down more. Alright, this is going to be our, this is going to be our, I'll just put a theta, and this is going to be our sine theta now. And for sine theta, it starts off at 0, so it's always opposite of the cosine. So it starts off there, but now we need to do it all the way up to 6 pi. So 6 pi, and I put the center is going to be somewhere around here, 3 pi. I'm going to put pi's everywhere, so this is going to be, next one's going to be a pi. Actually, let's see, the next one's going to be a pi. Yeah, this is going to be pi. Well, actually, I'll fix that up. The next one, this is actually better. This is like that, and this, and that. So this is 5 pi, this is pi, 2 pi, and this is going to be 4 pi, 5 pi. Fix this up. Alright, and then this one here, whenever it's pi, 2 pi, etc., it's always 0. So those are all the zeros. So we need to go somewhere in here. This is going to be the pi over 2. This is the peak there. In between those is where it's going to be. This is going to be 3 pi over 2. This is just added by pi or 2 pi over 2. So 5 pi, then add that again. Because the difference between here and here is pi, which equals to 2 pi over 2. So we can just add those up. So then another one here is going to be 5 pi over 2. And then over here is going to be, 7 pi over 2. These are the minimum and maximum. 9 pi over 2. And then finally this one is 11 pi over 2. Like that. So, and then this is going to be, the peak is going to be 1. The bottom, the minimum is going to be -1. Like that. So it's, and the peak is going to be at this part here. Minimum is going to be over here. And then peak is going to be always at these fractions. Yeah, then this one. And then this one here. And it's going to look like this. Goes up, goes down, goes up, goes down. Here, this goes up. And then goes like that. And then it keeps going. And yeah, it goes all the way back to the start. And then, so in other words, the maximum is going to be at, pi over 2. This is the maximums right here. So that's at pi over 2. I'll erase these now. So those are pi over 2, 5 pi over 2. And then we'll have 7, 5 pi over 2. We skip the 3 pi over 2, that's the minimum. Then we go to 9 pi over 2. Like that. Or, so these ones are for, basically, those are the maximums, but those are for 3 over 2 pi. So we need to get the t value, so that's basically t is equal to, solve for it. And then, so basically we cancel out all the 2's, and then multiply by 3. So it's going to be 3 pi. Yeah, this one, the t's will, for this one will be 3 pi. The next one is going to be, this is going to, you divide by 3. No, my bad. Yeah, so divide by 3. So here the 2's canceled and we move this over underneath, so we're going to get a pi over 3. or 60 degrees there. And then this is going to be 5/3 pi. And then the next one is going to be, well, 3 divided by 3 pi divided by 3 is going to be, well, 3 pi. Yeah. All right, so we can box these ones in. So these are t values at maximum. And now I'm going to circle those just so that it's not associated with those other values. This is just a signed function. And then we're considering this one for 3/2t, how it would be, and then from there just solve for t. And now the minimums. And yeah, when we look at the minimums, well, z is going to be minimized where sine of 1.5t is going to be the smallest, in other words, -1. And that's going to be at this right here. So we're going to write this as 1.5t equals to 3/2t, which equals to the minimums are going to be at here 3 pi/2. So right here, here, and here. Those are all the minimums. Let's erase these arrows. All right, let me just finish erasing those. And one more, and then yeah, so this is going to be at 3 pi/2. 3 like that. And then the next one's going to be 7 pi/2. Next one's going to be 11 pi/2. And then from there we could solve for t. So t is going to equal 2, cancels all the 2's out, and then divide by 3 on every single one. So this is just going to be pi. Next one is going to be 7/3 pi. Next one's going to be 11/3 pi. So those are the minimums there. So I'll box this out. And now note that these are precisely the values for which cosine 1.5t is equal to 0. And you can see that from above here. So again, these are the pi, 7/3 pi, and then 11/3 pi. Or we'll just look at these ones right here, 3 pi/2, 7 pi/2, 11 pi/2. Scroll all the way back up here. And this is at... before we even get to that, every single one of these are that. Yeah, so the minimum and max. So note that these values, I'll write here, both minimum and maximum, for which cosine 1.5 t equals 0. So if we look at the first one is pi/2. So you look at pi/2, and that's this one here. This is pi/2. So that's 0. The next one's going to be 3 pi/2. This is a 0. And we can see that here. Now let's write that. Yeah, so that's pi/2. So this one's pi/2. The next one's 3 pi/2. The next one is 5 pi/2, 7 pi/2. And then we'll go right here. This is going to be 9 pi/2, 11 pi/2. So I'll just write these all for completeness because it's already drawn out. It's going to be 5. And we just add 2 pi/2 to every single one. This one right here is going to be at 7 pi/2. And then this is going to be 9 pi/2. 11 pi/2. Alright, there it is. Alright, so what that means is, well, if cosine is 0, and we know that r, so r is equal to 2 plus cosine 1.5t. So we know that r, going back here, this right here, so r equals 2 plus cosine 1.5t. So in other words, we're going to have, so then that's equals to 0, so thus, I'll put a thus, r is equal to 2 plus cosine, and then I'll just put 1.5t, this equals to 2 plus 0 equals to 2. So at the minimum or maximum of the curve in the z-axis is when the distance from the origin of the polar equation, that's of the projection onto the xy plane, is when the distance is at 2. So in other words, it's somewhere around here, here, and here, and then from there we can see where is it overlapping and not. And here I quickly updated this to include these gaps right there. I mean, not the gaps. I made this so that this is more centered over there. All right, so it looks something like that. All right. So what I'm going to do is I'm going to copy. this, and then we're going to use a screenshot from my calculus book. I'm going to copy this. All right. All right, so continue further. So on the graph of the projection, these 6 points appear to be at the 3 self-intersections we see. And again, that's at this point, and this point. That's roughly where it is at distance r is 2. So roughly where r is equal to 2, roughly there. So those are the points, and then we could determine where the t corresponds and to which one's below and which is above. So comparing the maximum and minimum values of z at these intersections, we can determine where the curve passes over itself, as indicated in the figure below. So what I'm going to do is I'm going to put my sketch first, and then I'm going to do a screenshot of the calculus book solution manual. So here's my sketch that I did earlier. So put this like here. So, assuming that I'm gonna erase these. This was just a guide. So this was just a guide, like that. And now I'll erase this as well. What I had on the top. Erase the guides. That was the guide for the 120 degrees and 60 degrees, and so on. So what we have here, and I'm gonna add this eraser. There should be an eraser right here. Eraser, and I need to add it the normal eraser. This is point eraser, and make it smaller. Okay, I don't know why it doesn't allow smaller size. All right, yeah, should be good. So now what we have is, so I have an eraser, and so comparing the maximum minimum values at of z at these intersections, we can see determine where the curve passes over itself as indicated in the figure below. So if it's somewhere around here, here, and here, what we could do is, well, we know that at this point right here, this is going to be around 5 pi over, just about pi over 2, so roughly there. So pi over 2, well, becomes pi over 3. That's a maximum. So at pi over 3, around there, which is this is 60 degrees. Yeah, remember, pi over 3 is 60 degrees. Pi over 6 is 30. And then remember, the reason is if you multiply by 3 times, you get 180 degrees or pi. So in other words, that's pi over 3. That's a maximum. So that's a maximum. So that means, and that's the first loop. So in other words, this one's a maximum, and then the other one's going to be a minimum. Oh, well, we know it's a minimum because let's go back here. So at pi over 3, then doing adding a full 2 pi. So what I'll do is I'll go back to this pen. So if we have pi over 3. T equals pi over 3 is maximum, and then if we add a full 2 pi to it, so we have and then pi over 3 plus 2 pi, that's a 6 pi over 3. That equals to 7 pi over 3. So max, and then I'll erase this like that. This one here, this is 7 pi over 3, and go back to where it was. This is 7 pi over 3. This is a minimum. Yeah, so I don't know why it's not writing anymore. Yeah, this is a minimum. Yeah, so in other words, this is a minimum. I just wanted to illustrate at least the first point simply. All right, so this is a minimum right here. Okay, this is a minimum. So in other words, the one below it is a minimum, so we can go and use our eraser and basically erase. I'm going to erase this whole thing. Yeah, so erase that whole thing, or make it a bit closer, and erase it. I'm going to erase right here. Yeah, so actually, I'll just erase it one time. I don't know why it doesn't do it. Okay, there's the eraser. I'm going to erase every single point right here, and erase this one as well. Alright, so now I'm going to change this eraser. Alright, anyways, now that I've changed that, so basically this one is a fixed line. The one below it is is the minimum. That's the maximum, is the minimum. And now if we go over here, let's take a look at when this is at pi. So minimize, so t is minimized at pi. So in other words, and then at 3 pi is maximum. So that's a full 2 pi. So in other words, the one after it is that. So this one here is below, then goes above. And now this part right here this is in this quadrant, so that's going to be just below 2 pi there. So let's take a look at this part right here. So it's a maximum at 5 over 3 pi. So that's closer to 6 pi. So that's going to be a maximum. And if you look at the alternative, this is 11 over 3 pi. That's a full 2 pi around it. So this one's going to be a minimum. So at this quadrant, when it's getting closer to 2 pi, is a maximum, so it's going to be maximum, goes above. And then on the second time around is 11 pi over 3. That's going to be a minimum. So in other words, it's below. So there it is, how it looks like. This goes in and out like that. So it's epic stuff there. And all right, here going further. So yeah, here's a sketch from my calculus book solution manual, and it's exactly the same thing we have here. So it goes above, below, it goes above, and then it goes below, and then above. Above, below, above. Yeah, so above, below, above, below, above, below. And again, it's the same thing. Above, below, above, below, above, below, and so on. Keeps going on and on. There it is. Pretty cool stuff there. And it's, again, same thing as this one. Just a bit more neater here. So, and here is my calculus book solutions manual. It uses, it provided these graphs as well. So we show a computer graph, a computer drawn graph of the curve from above, as well as views from the front and from the side. So this is how it looks like here. This one, yeah, so this is pretty close, but this is, note that the Y is on the bottom here, the X is on there. And notice that it looks very similar to ours, except there is these little inflection points. So it goes like this, and then there's an inflection. There's a big blob, and then inflection. Big blob, then inflection there. So that's pretty cool. And then there's, yeah, it looks very, very similar, but then look at how the shape is. Yeah, so it has an inflection point. Yeah, so yeah, I mean, it goes like this. It goes like this, and then inflection, and then inflection. So every time there's an inflection point. Ours didn't have that much detail, because we were just trying to draw it by hand. So again, this is why computer is going to be much more accurate for these complicated graphs. And here's the front view, looks all like this. So then from the top view, there's no way you can tell that this is going to look like that from looking at this. And side view looks like that, looks like kind of like a fish or a missile. So the top view graph shows a more accurate representation of the projection of the trefoil knot onto the XY plane. The axes are rotated 90 degrees. Just a note here, this is X, this Y, as opposed to X and Y. All right. And yeah, so it's rotated, so 90 degrees. It should be over here. Make it upside down, yeah. All right, and note the indentations or the inflection points the graph exhibits at the points corresponding to r equals 1. So at r equals 1, so which we ignored here. So this part's right here, the closest point here. This should be an inflection point. It should be like something like that, bends over. All right, and yeah, that's r equals 1. This is r equals 1. So at these at this point right here. So that's quite fascinating stuff. Yeah, so that's like that. And corresponding to r equals 1. And finally, we graph several additional viewpoints of the trefoil knot along with 2 plots showing a tube of radius 0.2 around the curve. So here's how this looks like. You can move it around. Looks pretty cool. And now here it is with the tube, so you can see it going in and out. So it goes like that. It's pretty epic stuff here. In our case, we would start off from here, above, below, because it's just, because in our case, our graph, the arrow was pointing to the right, or if you look at the two blobs, so it's my computer's loading up. Yeah, this right here. So it looks like, so it has a direction. In this case, if you draw a triangle, it points to the right. Like that. It's just point to the right, just so we know that that's the one we were looking at. And so yeah, again, and then there it is in 3D. You can see it going in and out. So pretty amazing stuff. So and here's a trefoil knot plotted in GeoGebra. So if you type it all in here, and I graph it from 0 to 6 pi, and it loops around. So it looks pretty cool. And here's a top view. There's indentation and so on. And there's from side view. Another front view, or yeah, that's front view because that is the Z. There's the X. And note that GeoGebra doesn't have a tube command, so I had to create a surface via Grok AI. Just asked it that has a circular cross section around the trefoil knot curve. This one's a bit simpler than the other one. I did this in my earlier. I think example 7. So basically, this one, the whole I just used Grok AI to tell me what to do, and basically it has this is our parametric equations. I don't know why it's not writing. Okay. Yeah, this is our parametric equation. Then it adds a second parameter u. So it adds 0.2 cosine u on this one here, and then 0.2 sine u. So it keeps adding on the x and y coordinates by u, where u wraps around a circle. So from 0 to 2 pi. So it somehow does that and makes a surface. And you could see it in there like this. And it looks like this. So yeah, there it is. This goes above, below, above, below. So above, below, above, below, above, below, and so on. Loops all the way around. There it is from a 3-dimensional view, and so on. And also, here's the same plot in Desmos' new graphing calculator, which has a tube automatically in. Yeah, so in Desmos, yeah, they just created a new one, trying to compete with GeoGebra. Because I used to use Desmos for 2D, and I'll go over here, and I will use Desmos later. But anyways, so here's the graph, and here it is. You can play around with it. And and it's pretty giant. So there's all the equations. Let's close that all up, and you can move it around. All right, and then what you could also then you go all the way to the top, and there it is, perfect shape. Absolutely amazing. And yes, that's amazing stuff there. So 3D with the tube, you can see how it actually is. And if I can remove the surface, there's the curve. There's a surface right on top of it. Perfect setup there. And the surface just makes a cross-sectional area anyways around it. So another thing I wanted to show is if you add, let's say, 5 pi, and then graph it out, see how it doesn't fully loop around. So I think I didn't include, did I not press enter? Yeah, I need to press enter. 5 pi, enter. Alright, so we added 5 pi. Let's see how it cuts off. So it's still graphing it, so I don't know what's going on. It shouldn't graph it. Oh, that's T. Okay, so it's T, yeah, T goes to 4 pi. So because remember, the other one is the 1.5 T is from 6 pi. So I'm going to put 3 pi. Yeah, and yeah, there it is. So see how it doesn't fully loop around. So we need another 4 pi there. So we need 4 pi at least. Yeah, so there's full setup there, and then there's the setup there. This is the surface, and again, yeah, it takes a lot of computing power. Anyways, that's how it is. I'm gonna close this, leave, and now here is the Desmos calculator. You can also do that in here. You just plug it in. There's put the parametric equations. It automatically draws this, and again, this should be in 4 pi. And if you go erase to 3, there it is. Cuts it off. This is 4. Yeah, so that is. It should be like that. And yeah, it looks like the knot there, but yeah, some pretty epic stuff there. Alright, I'm gonna close, I'll just leave this open. Alright, so yeah, epic stuff there.